So I'm going to do a talk on relational versus NoSQL databases. This is going to be high level. It's just a tour of what they have to offer. So don't expect anything too technical. I'm Jason O'Donnell. I am a Postgres engineer for a company called Crunchy Data Solutions. We do security-related development for Postgres, mostly for the government. Before I worked at Crunchy, I was a systems engineer at State Farm, where I did cloud infrastructure for both Postgres and React databases. So I'm going to start with relational databases, and probably everybody in here is well aware of relational databases. So Edgar Codd was a English computer scientist who worked for IBM. He studied in Ann Arbor, Michigan, and when he worked at IBM, he wrote a paper called Relational Model of Data for Large Shared Data Banks, which was the beginning of relational databases. This was in the mid-1960s. He worked at IBM for a while, and he actually kind of made IBM mad, because at the time, they were trying to push a different product that wasn't his model, and he was actually going to customers and telling them that his model is way better. So IBM started developing new databases, and they were actually kind of isolating all of their developers from him so that his radical ideas wouldn't make it into their product. But eventually his product won out. He left IBM, started his own company, and I think Oracle bought it in the end. So what came out of his work at IBM is the relational database as we know it. Tables are made up of columns and rows. The columns all have attributes that specify the kind of data types that can go in that column, and then the values are inserted into rows. And any kind of queries that we do against the database come back as a view. And we know our relational databases, the big players today: Postgres, MySQL, Oracle, and MS SQL. The reason that relational databases were developed were because we really wanted consistency with data. We wanted to make, if we had a transaction, we absolutely wanted to make sure that that was permanent. So relational databases follow ACID properties. And ACID means atomic, consistent, isolated, and durable. Atomic is all or nothing. When you do a transaction against the relational database, if any part of that query fails, the entire thing is rolled back. So all or nothing, there's no partial successes. Next is consistency. We want to take the database from one valid state to another. So that means whatever changes you're imposing on the relational database have to be within the rules of the system: triggers, constraints, data types you use. Everything has to be valid. We want to isolate our transactions, so we can't have like two parts of a system accessing the same data at the same time. So things are done sequentially. When you access a row, a specific row, there's a lock put on that row, and no other parts of the system can use it until it's unlocked. And we want it to be durable. Durable means that when we commit something, that it's in permanent storage. It goes to disk. So usually, like a lot of relational databases will write to a log first before they actually change the data. In case that there's a power loss, when the database turns back on, it'll chunk through that log, and it'll do everything that's in the log, so that makes sure that the data is there and it's up to date. So some of the advantages of a relational database is that because we can write SQL queries that are very complex, the data only has to be in one place. We can combine our tables and access the data without actually having duplicate copies of that data. So that's important because it's efficient for our storage. It simplifies our queries. Updates and deletes only have to update the values in one place. And changes will, if there's triggers on the change, it'll follow those triggers. If there's constraints, all that stuff is applied. Like I said, rich and complex queries can be done in SQL, and that's kind of the big picture. We can take tables and join them together like they're one table, and do amazing things with our data that isn't necessarily together. Relational databases offer a lot of security built in. For instance, users, roles. You can do really nice nested hierarchies of positions within the database, what people are allowed and can do. And there even gets a little finer with row level security, where you can define what rows people have access to, what kind of access you need to get data out of certain columns in tables and schema. And because it follows ACID properties, it's reliable. So mostly these are the advantages of a relational database. Disadvantages, though, relational databases are extremely complex. They've been around for a long time. There's a lot of things working behind the scenes. I go behind the covers of Postgres every day, and it's not pretty. It's extremely complicated. Because that relational databases are ACID compliant, means that they don't horizontally scale very well. When you have a bunch of computers that are all working together in distributed computing, you can't absolutely guarantee that consistency of data will be there. So in relational databases, they scale vertically because you want all your reads and writes done on one machine. So that server has to be big and has to be beefy. So relational databases aren't very good at horizontal scaling. Your data structures are set in the database. When you compile the database, everything that's in there is what you have. If you need more data structures, you'd have to recompile the database, add them yourself, and it's not very flexible with the kinds of data that you will need. Because of ACID properties, availability is tough. Like I said, vertical scaling means that you'll only necessarily sometimes have one server. If that server goes down, your availability is 0. So if you were able to scale horizontally, you would have more availability, but relational databases can't do that as easy. There's a lot of overhead. Relational databases are big because of all the things that they can do, and that is not necessarily required for every application, especially, we'll see later, some of the applications you can build without a relational database. And there's only one interface to a relational database, and that's SQL. You can't really get the data any other way. You have to get it through SQL. So, disadvantages. So NoSQL databases. They've actually been around a lot longer than people believe. A lot of people, they haven't really become popular until recently, probably like the mid-2000s. But in the 1960s, there were NoSQL databases. Actually, at CPOS, in Mike Barlow's presentation, he mentioned MUMPs in the healthcare industry. They used that as their document storage, and that dates back all the way back to the 1960s. So it's pretty old, but not widely used. The reason it became big, though, it was mostly because of the big data boom, and mostly by the big tech companies like Amazon, Google, and Facebook. Specifically Amazon, though. Amazon DynamoDB paper is really excellent to read if you're into white papers. It's a really approachable white paper in the computer science world, so highly suggest checking it out. NoSQL databases are simplistic in design. They're supposed to be. They were built that way because they don't want the overhead that you get from a relational database, and they also don't want the need for administrators to have to run it or take care of it. It's kind of focused more towards developers to not get in your way. In design, NoSQL databases are horizontal scaling, so it's distributed computing. You'll have servers in a cluster, and you can add and remove servers as you need, and everything's built in. It will replicate data for you. It'll repartition data for you. So that's kind of built in with NoSQL. And because of that, you have a lot more availability control. We have more servers in distributed clusters, so you get higher availability. But you get higher availability for giving up some consistency because you're in distributed computing scheme. NoSQL can support a lot of different types of data structures. So that's one of the big advantages of NoSQL is I mean, in the end, it's just being stored in binary, but it doesn't really have any restrictions on what you can put into it. And we'll see some of that when we dig into them a little bit more. And the interface varies. It's not, I should have mentioned this earlier, NoSQL is not necessarily meaning there is no SQL. It's not only SQL. You could use SQL. Some of the backends of NoSQL databases are actually relational databases, but they're using them in a way that it's a little not, I don't know, it's not standardized, I guess. But they actually interface to the relational database for you and provide you an API to leverage it. So NoSQL databases are governed by the CAP theorem. And the CAP theorem is consistency, availability, and partitioning, but you can only have 2 of these at once. You can have close to 3, but 2 is mostly what you get. And NoSQL database in specific give up consistency for high availability and high partitioning. So consistency, same data, all the nodes see the same data. Availability, every request is going to get a response. And partitioning is in a cluster, that data is distributed, and if any of those servers go down, that data can be retrieved from somewhere else. So high availability. A quote from the DynamoDB experience at Amazon has shown that data stores that provide asset guarantees tend to have poor availability. And that's pretty obvious. I mean, if you're going to if you're going to put all of your eggs in one basket in a vertically scaling server, your availability is going to suffer from it because you only have one server. So if that goes down, your availability is 0. So there are a lot of different types of NoSQL databases, but I'm only going to go through 4 of the major: key value, document stores, column-based, and graph-based. So key values are probably the simplest data structure in a NoSQL database. We know them as maps, dictionaries, tuples. Basically, you have a key that's unique, and then you have the value of that. And that value can be anything, though. You can have, like in this example, you can have a lot of customer data in like a JSON format or an XML format or even binary, strings, whatever you want. You can lexicographically sort the keys, so it makes operations quicker. If you sort them as you insert them, retrieving things is very fast. The cool thing about some of these databases, though, is that we give up some consistency for this high availability, but we could tweak the database to be more consistent and give up some availability for that. So there is a little bit of room to wiggle there. And a lot of these databases, the backends can be pulled out, and you can either put in an all-memory database in the backend and use it for like caching and queues, or you could use solid-state drives. You can use spinning disks if you have, say, just a lot of data that you need to store. And some examples of these types of key value databases are DynamoDB, Redis, Oracle NoSQL, and CouchDB. And you'll see some of these databases actually will appear again because they too can change their storage depending on your needs. So some of the applications you could use these for, like I said, caches and queues, a lot of real-time information, like application, like state machines. One thing I thought of was like on Facebook, you have like the trending topics thing up in the top right. That could be easily solved with a key value store. So next we have document stores, and document stores they build upon the key value concept, but instead of having simple values, they have composite objects in there, usually encoded in like XML, YAML, JSON formats, binary JSON. Every document is going to have a unique key because you need a way to retrieve it. You generally use an API query to get the data out. And the document stores give you some extra organizational tools that can make your queries more efficient. So you can put things in collections and tags. They can have hierarchies. So there's a lot of interesting performance you can pull out of this. And like CouchDB has already been shown, but now Mongo, and actually Lotus Notes is a document store, and it's been widely used for a very long time. So we can use this for a lot of nested information like JSON objects. It's obviously very JavaScript friendly. One thing I didn't mention, that we can actually put actual documents in here. So PDFs, I mean, it's just binary when it gets converted into the database. So put whatever you want in there. Templates to web pages, you can pull out all sorts of kind of like handlebars kind of stuff into your, your applications. So we have column stores. Column stores look a little bit like relational databases, but they have one very big difference. You have your columns and your rows, but in your rows you can have any amount of columns you want. There's no, it's just a way of organizing your data by a column, by an extra key, but you don't actually have to have the same columns in every row, so you could store different information in every single row. But the whole point is that you have this column family of data that's sort of related, but you put all the data that you would normally pull out into that column, into that row, so that you retrieve it all in once. But it's a little bit more organized. Like I said, it doesn't require the same columns as the other rows. You can add and remove columns from any row at any time. So this is supposed to be one of the highest scalable data structures you can have in a NoSQL database. It's really good for sorting and indexing, and you get a lot of granularity because of the fact that you can put as many columns in any row you want. Some of the big players in this space are Cassandra, DynamoDB, HBase, and Google's Hypertable. And these are generally good for large amounts of data. Like I said, you're organizing the data, but you're also retrieving large amounts of data at once. So it's really good for big objects. And Reddit pretty much runs off of this concept. Netflix, all of their videos and movies are all packaged into these column families in rows. And Twitter does it. I think they do it for like messaging or something, I can't remember. And then last we have graph stores. So this is more spatial related information, things that are not necessarily one-dimensional. Basically you can store entities and the relationships between them. And the interesting thing about this is the entities can have as many relationships as they want. So traversing relationships is super fast. You can get right to the data that you need really quickly because of the amount of relationships you can have on an entity. And some of the big players in this are Neo4j, Infinite Graph, and OrientDB. You could do, Google Maps runs off of this spatial kind of storage. You can store things that are not necessarily easily transcribable to a one-dimension data structure, like social relationships and network topologies, things like that. So the advantages of NoSQL is you can kind of tailor these to your application. You're not stuck into the rules and data structures that a relational database gives you. And we don't always need that. We don't always need the overhead of a relational database to solve our problems. A lot of the advantages of NoSQL come out of the fact that Amazon uses them for tons of microservices that, I mean, if they had relational databases running in the background, it would become a nightmare to maintain. So they kind of work in conjunction with relational databases to run a ton of different services without the overhead. Because of the way that NoSQL databases are put together and some of the things that you can do with like sorting keys lexicographically, some operations are actually more efficient than relational databases, and some operations in relational databases are more efficient than NoSQL. So there's some trade-offs there. You get a lot of high availability because you're working in distributed computing, and it scales horizontally really well, and you get tons of choices of data structures and different backends you can use, different kinds of, replication, things like that. There's a lot more choices in NoSQL. Some of the disadvantages is that most of them don't come with security built into the database. Relational databases have a lot of security usually built into it, but NoSQL generally requires the API to do the security for you, or the operating system to do security for you, the web server, things like that. You get eventual consistency. So if you have anything that requires reliable data, this is not going to be good for you. So you have to kind of, when you're building with these NoSQL databases, you have to think beforehand before you do it, because you're going to be designing your application to fit into this NoSQL mindset, instead of with a relational database where you can do lots of complex things pretty easily. It's not as mature as relational databases. I mean, relational databases have been king for 30, 40 years. So because of that, you don't get as many experts. And one of the things that I had a little bit of trouble putting in here, design goal is a little administration. I'm an administrator and I love administrating, so that kind of sucks for me. But if things go wrong, I mean, you really need to know, you need to have people who know what's going on. And if you rarely ever touch the database or administrate it, it could be a nightmare for your application. So pretty much, relational databases, you have your set types, and in NoSQL, you have key value, graph, column, and document-based databases. Relational has a lot more history. NoSQL really doesn't. Your storage models are more flexible in NoSQL compared to relational databases. There's some scaling trade-offs between the two. In relational databases, your data manipulation language is SQL, and that changes in NoSQL to more of an API. You're going to make consistency trade-offs, and I am kind of painting a black and white picture of these two, but really widely now that they're being used together. Relational databases still have a place, and NoSQL definitely has a place. That's all I have.